My name is Sir Latham Wynn. I'm a PhD student at the University of Nevada, working with Professor Kerry Ryan. Our group is focused on the non-structural walls, and also the stairs are included in our scope. So each of the non-structural walls have some way of accommodating the drift or accommodating the drift demand on the building. So because the building is designed to uh, have large displacements because of the rock and wall system. My role specifically, I focus on the glass curtain wall facade on the northwest side of the building, which you can't see behind this in this from this view. The curtain wall system essentially is a steel frame glass facade. It's 2 stories. It's a fire rated curtain wall system, so it has thicker glass and steel mullions.
That's the really cool orange frame on the northwest side.
Yeah, the cool orange frame.
Illini orange.
The Illini orange, yes, sir.
I mean, we'll claim it as Illini orange. It's probably actually OSU orange, but we'll say it's Illini orange for us.
Yeah.
Awesome. So what do you think of the test today?
Oh, the test was pretty impressive. My favorite has been the Chi earthquake. So
That was nuts.
yes, the way the building whips is pretty impressive, and it's really impressive how the non-structural components are able to accommodate the drift and those, because it looked like it's a pretty high demand on components.
Yeah, did you get a chance to walk up through the building and see how your components that you worked on did?
Yeah, they did really well. There you can see some like you can see how like the sliding of the certain clips in the CFS2. You can see those doors opening. We call it CFS2. It's a cold form steel frame exterior wall. It's balloon framed, so the framing spans 3 stories.
Oh wow.
So the way it's designed, the exterior wall is allowed to slide across this unit strip, which is attached to the floor slabs.
Mhm.
And then even during the testing, you can see like there's a joint that opens up
Mhm.
that allows for corner compatibility.
Cool.
So it's pretty cool to see, and you can see it in the earthquake. See the doors opening up, and I think in the Chi earthquake, the top drawing a blank, the top panel,
Mhm.
it actually stayed open.
Wow. Oh, that's awesome. Yeah, it's been amazing. Like to see like all the windows are still in there, all the doors still work. Like the stairs are still together, all the railings are still attached. Like it's really like in a normal building that's not designed like this one was. All of that would like there'd be glass everywhere, there'd be doors all over the place, and everything still works. It's awesome.
So what's our goal is resilience. So what we learned is that we learned from previous earthquakes is that even the resilience isn't only about the structural components. You also have to consider the non-structural components, because even in the Northridge earthquake that we ran today, 50% of the repair costs was not structural damage.
Oh wow.
So it's a pretty important factor to consider when thinking about resilience.
Yeah, I mean, you think of it, imagine this was an actual, apartment building or a commercial building or something like that. I mean, this would be many millions of dollars to construct it. And if it was subjected to an earthquake like Northridge and not resilient like this, it'd be, total loss perhaps. And, many millions of dollars to tear it down and rebuild it again. But this is maybe a few thousand to repair some drywall, and that's
Yeah.
about it. Like rehang some pictures.
Exactly.
So it's really amazing. What year in school are you? What's next for you?
I am in my second year of my PhD. So once we collect all the data from this test, I'll just be processing, writing
For a
papers.
long time.
Yeah.